All right, folks, for this last video for 2.4, we're going to jump into some problems about springs. And here we go. So first one is a spring that has an unstretched length that we know, a force constant that we know, and we're looking for the force needed to give the spring a length of 15 centimeters. So let's talk about that after we do a free body diagram. So we pull with an applied force F on the spring, and as a result, the spring will match that force. The reason that is because we want the spring to have a specific length, and that means we have to pull on it with a specific force. We can also see that using Newton's second law. So we're going to set up an acceleration of 0. The acceleration would happen as you're lengthening the spring, but a specific amount of force is going to give it a specific length. This applied force will be equal to the spring force, and the spring force is equal to K times displacement. So with this line of equalities here, you can see that a specific amount of force is associated with a specific amount of stretch. Because we know the stretch and the force constant, we can figure out how much force is necessary. So this problem is relatively straightforward as long as you understand that the way the spring force equation works, there is a specific force required for every possible amount of stretch for that spring. The K is 3.5, and then to find the displacement of the spring, I need to subtract those two lengths in meters because I have the unstretched length and the stretched length. So it's going to be 0.15 minus 0.08. And so that applied force is going to be 0.245 newtons. And again, like every spring, based on its spring constant, you can figure out the exact amount of force necessary for an exact amount of stretch or displacement. All right, this next problem is one that looks a lot more complicated than it is. You just have to carefully manage the question. So this one is hanging springs, hanging masses from springs. So we have 0.20 grams and the length of the stretched spring with that, and then adding 0.40 grams of mass to the spring and having it stretched to a new length. And so our job is to calculate the force constant of the spring. This is something that comes up pretty typically, the spring force, a spring being used to suspend masses. And so the net force in both situations is going to be equal to 0. So the spring force is going to balance the force of gravity. So when something is hanging at rest, we can start with this idea of equilibrium, and in this particular case, set these two forces equal to one another. Now, the spring force is equal to K times delta X, and the gravity force is equal to M times G. And so what I want you to see with this equation is very much the same as the last one. There is a specific amount of stretch now associated with a specific mass being added to the spring. So no matter what situation the spring is in, initially, if you add a specific mass to it, it will stretch by a specific amount. In other words, those variables are proportional, and so I can be selective about what I analyze in that situation. What I want to show you is that while we don't know the resting length of the spring, what we do know is the length of the spring before we put 0.40 kilograms and the length of the spring after we put 0.40 kilograms. So I'm going to use a mass of 0.40 kilograms for this entire problem. I'm going to ignore the 0.20 because I can't use that yet to find the equilibrium length. So I'm going to use this equation, and it's going to say K times delta X. So delta X, that's going to be the stretch due to the 0.40 kilograms. That's going to be 0.205 meters minus 0.18 meters. That is equal to 0.40 kilograms times 9.8. And so this is something where I just want you to see that your job is to find a situation where you know the amount of stretch and then use that to solve the problem. So I can calculate the gravitational force, and then I can divide that by the stretch in the spring, and I get a K of 156.8 newtons per meter. Now, if If you didn't buy that, meaning if you don't believe me that we can just use the stretch of this extra mass and not involve the original mass, what I want you to do is to use this value of k to figure out the resting length of the spring. And you're going to find that it is, sorry, I did it myself, it's 0.1675 meters. And again, just to check, the final situation that this spring is in is that there's 0.60 kilograms on it. So if you use this like resting length of 0.1675 meters and use this as the final length, you should see that this force constant times the amount of stretch to get to 20.5 centimeters is equal to 0.60 kilograms times g. Up to you. All right, last question. I wanted to show you something where there was acceleration, and this is another kind of easy one once you can understand what's happening. So this is an unstretched spring with a force constant. It's attached to a cart and pulling the cart along a flat, smooth surface. So smooth means no friction. We have an acceleration of the cart, and we're looking for the stretch in the spring. So if it is a smooth, flat surface, then that spring force will be unchecked by any other force. If I want to complete my free body diagram, I can put the normal force and gravity forces in, and then I can really just focus on that one spring force. So the net force on this cart is going to be just due to the spring force. So the spring force is going to cause acceleration of that mass. Now the spring force is equal to k times delta x, and that is equal to the mass times the acceleration. So I'm going to use this to figure out the stretch of the spring. So I'm going to put 120 times delta x equals 0.45 times 1.4. All right, so I do 0.45 times 1.4 divided by 120, and I get a stretch that's super tiny because I made these numbers up on the spot and didn't check them very carefully. And so we get a really tiny spring stretch that is 0.5 centimeter of stretch, not very much. And so that's it. So when there's acceleration, the acceleration can still be caused by a spring that is at rest, essentially. It's not stretching anymore, but it's just accelerating because in this situation, there's no force that's able to balance or counteract that spring force. And so that's enough to get you started, and then there's some, for sure, trickier ones in your packet.